Well, hello again. I'm doing reaction mechanism again, part 2. And one of the things that you've also must have covered by now, my students definitely have, is reduction using sodium borohydride or lithium aluminum hydride. But I think in your syllabus, more emphasis put on sodium borohydride. Now, we all know, well, let's say up to now, that hydrogen, which is 1s1, usually turns to, or prefers to be turned into hydrogen plus, i.e. losing the only electron that it has, and becomes, 1s0, basically. And that's why hydrogen is put in group 1, above group 1, even though it's not a metal, but it has a tendency to lose an electron to turn into a proton, because that's the only thing which is left. When you lose the electron from the outer shell, what is left? The only thing that you have is the nucleus, and the only thing that you have in the nucleus is a proton. So sometimes it's referred to as proton. But why not 1s1 turning to 1s2? Why not gaining an electron? Surely we all know that, the first shell, 1s2, is also stable. But like I said, the tendency of hydrogen is to lose electrons rather than to gain. It wants to turn into a proton rather than a hydride ion with a negative charge. You see, even when I write hydrogen, almost instantly plus comes along. Hydride ion, why not? 1s2. So why is this a reducing agent then? Why is it producing H minus? Well, the thing is, under normal circumstances, it loses an electron, but not when it is sitting next to sodium. You see what I mean? It's a sodium that wants to lose an electron. It's group 1. It's a very, very reactive metal, and therefore hydrogen on this occasion gets humbled and gain an electron. How do we show that in chemical reactions? When we talk about reduction, we just, the same way that we use oxidation as uppercase oxygen in square brackets, we write uppercase hydrogen in square brackets. So that would be our symbol of something that is being reduced with hydrogen for the hydride ion. Okay. So when actually do we do these kind of reactions, or what kind of products can we form? Do you remember when we had, for example, methanol, and then we oxidized it and turned it to methanal, right? Plus water. Well, if we oxidize it and turn it to methanal, can we not reduce it and turn it into, well, yes, we can. Why not? But how do we actually do it? Well, let's see. You have your aldehyde there. Let's draw it slightly better so you can actually see what's going on. What do we need to do? Delta plus, delta minus, right? So H minus times. Doesn't that make sense? And then H. Now you have that bond has broken, you get a negative there, your hydrogen is sitting there, and then the other hydrogen sat there, right? And then this is going to find a hydrogen from somewhere, maybe water or alcohol. Yeah? Again, delta plus, delta minus. And then it's going to turn into, I'm trying to do the color codes here so you see where things are coming from. You get your alcohol back. I mean, if you can oxidize primary alcohol to produce aldehyde, why can't we reduce aldehyde to produce what it used to be before? And this, of course, is reduction. Okay? But can we actually name it something else as well as reduction? I mean, what is this guy? Is it a nucleophile or is it an electrophile? Does it like electrons or does it like a positive center? It's a nucleophile, isn't it? So what happens then? Is it going to go in there and substitute something? Or is it just going to go in there and just add itself across? It just goes in there and adds itself across, doesn't it? So it's a nucleophilic addition. It's not substituting anything, is it? It's a nucleophile, nucleophilic, and it's added itself. So nucleophilic addition. You see, each of these names, when you think about it, it's quite rational. Yeah, so you don't need to memorize it. You can work it out if you think about what you're doing. All right? So that is reduction. That is reduction. Where else in the syllabus did we come across nucleophilic addition? Towards the end of the Module 6, aromatic synthesis, you probably were introduced to nitriles, CN. The inorganic CNs are referred to as cyanides, like potassium cyanide, but the organic ones, the functional group is referred to as nitrile. So let's explore that. Now, let's say again that you have an R group, and a hydrogen there. It could be an aldehyde, it could be a ketone. And then you react that with hydrogen cyanide. Hydrogen cyanide. Hydrogen gives up its electrons to cyanide. So basically you have Cn minus. Carbon triple bond, yeah? Hydrogen. So what do we have here? Carbonyl functional group, remember? Delta plus, delta minus. So this guy has turned into now Cn minus, and don't forget that H plus somewhere in the background. So the reaction mechanism. Right? So what do we have? RCO minus. Hydrogen is sitting put, and then you have that Cn. All right? And then that hydrogen over there, remember that guy? So what do we have? So what is the significance of this reaction? First of all, this is again a nucleophile that just goes and adds itself across. The significance of this reaction is that it adds whatever number of carbon atoms you had in the backbone, now you have one more. isn't it? So it's an addition carbon to the backbone. But then it is also interesting to know that now that you have these nitriles, so if you have R, COH, HCN, right? If you reduce it, like nickel and hydrogen, or sometimes sodium borohydride as well, you produce carbon OH, H, R. Your carbon will take 2 hydrogens, and your nitrogen will take 2 hydrogens. Oh, so we've actually converted it to the corresponding amine by reduction. But obviously there are 4 hydrogens there, so 4 hydrogens. It's quite obvious. Its hydrolysis will result in the formation of a corresponding. So basically, your CN becomes COOH, corresponding carboxylic acid. So you've the reactions of nitriles is also enormously important, as it can lead to formation of amines or carboxylic acid with an extra carbonate. What about if instead of hydrogen cyanide, you use potassium cyanide, for example? Right? So in potassium cyanide, you have Cn minus and K plus. So it does what it did before, delta plus, delta minus, and then you get your O minus, but that sits next to, the only problem is that it sits next, it produces a corresponding salt. So what do you have to do now? You have to add H plus, so the H plus will go there and kick this potassium out and turn it into what your desired product was. So if you use sodium cyanide or potassium cyanide, it has to be under acidic condition, because otherwise you produce the corresponding salt. Okay? So that's another one. And the next one I want to perhaps go through and wrap this up is electrophilic substitution. Electrophilic substitution. We discussed that in nitrobenzene, the very first lesson that I did in aromatic organic chemistry. And just to reiterate, that you have to have an electrophile. An electrophile could be a chlorine plus, could be an alkyl plus, could be a nitro plus, something with a plus charge. I'll just reiterate. Go to the first lesson I put in this series, and then your benzene ring that has got a lot of electrons in it. Electrons come, what did I tell you? Come from where they are towards where they want to go, whether it is NO2 or Cl plus or Cl plus or whatever. Don't forget the intermediate. That arrow means a pair of electrons is coming out to form a bond with that. So you have to show that a pair of electrons have been lost. Yeah? Remember what I told you from second to the 6th position? And if electrons have been lost, therefore you have to show that something's lost, electrons lost, therefore it's positive percentage. But in this case you have NO2 over there, and then this is the intermediate, and then in order to reestablish the integrity of the compound, the electrons from carbon hydrogen goes in there, hydrogen comes out as H plus, and H plus, please remember, we react with the sulfuric acid HSO4 minus that we use as catalyst. Go back to the very first lesson on nitration of benzene, and then your catalyst is regenerated. Okay, your catalyst is regenerated and you produce the nitrobenz. So that is just a reminder of electrophilic substitution. Each of these names are absolutely logical and rational, and that is that. That is that for the day. Okay, thank you very much.